Our next speaker is Federico di Vruno from SKAO, and he is also a co-president, co-director of the IAUS. Thank you very much.
You know me already, don't waste time. All right, let me put this thing so I try to make it in time. Okay, hi everyone. You already know me, so I'm just going to go ahead. This is a little bit more technical, but I'll try to explain a little bit, and I hope you can all understand. All right, so I'm going to talk about modeling satellite constellations for radio astronomy impact studies. So I'll try to explain why we need to model and understand how we see satellites. This is the agenda, so I'll try to explain a little bit on why, then how the model was developed, how we did some observations to try to verify that the model is correlating, or we were proving that the model kind of works, and then what are the further applications of this kind of modeling. So let's go to the motivation. So we are all talking about satellite constellations and how many they are and where they are. So that's one of the things that more or less we can say where satellites are, right? We have TLEs, we have supplemental TLEs, this information of where satellites are in space, and we can propagate this, we can calculate all of this, right? With more or less precision, we can do that, right? So you see there, this is only an example. This is Starlink Phase 2 constellation, the whole constellation, 30,000 satellites, or 30,000 something. And what is interesting is that, for example, if you have your telescope there, the sky that you see from that position in the Earth, you will see these three lines, and those lines are related to the geometry of the constellation, right? The different inclinations and so on. And that basically translates into something like that on the sky. Right? And this is density, right? This is density of satellites in the sky. So what this is saying is that if you're looking straight up in your sky, you will see less satellites than if you're looking lower on the horizon, right? Which is like intuitive. But also you have these lines where there are more concentration of satellites, right? So we can model this, and this is more or less okay until you go into very narrow field telescopes, and then you need a lot of precision, and that's maybe something that someone else will talk about. Right, so, oops, where are we? There, all right. So, sorry, this is supposed to be moving. There, okay. So now we know where the satellites are, and what we need to understand is how a radio telescope sees a satellite, right? So this is a very nice animation from our friend Benjamin Winkle that is showing the sky there in azimuth and elevation, and the shading you see there is depicting how a radio astronomy antenna works, right? So you have an area where you're pointing, that you have a lot of gain in that area, and then you have some side lobes or other parts of the sky that you still see things, right, from other directions. You're pointing there, but if something is there, you still kind of see it. But if you see, again, the movie, note that these spikes in received power are when these little dots go close to that beam, right? There, for example, right? So when you get one of these things close to the beam, you get a lot of received power. And this is only considering the gain of the radio telescope. Right? So this is thinking that every single satellite is like an isotropical transmitter. So wherever from any direction you see the satellite, it emits in the same way, which is a very bad assumption, but it's there, right? So we can do that. But the situation is a bit more complicated because satellites, and especially the new ones like Starlink, have these steerable beams, right? So we actually don't know where the beam is looking at, right? We know that they work in this way. We know how many channels they have, what are the frequencies they use, but we don't really know how many beams per channel the satellite is producing, for example, right? You see in this very nice animation there that the satellite can produce 4, 8, 16 beams, and that will change how much power you will see from the satellite, and it also will change depending on where are you and where the satellite is beaming at, right? Chris was talking about that before, of arguing to try to get the beams away and saying where the telescope is pointing at, so those satellites don't point at you, and so on. So, but at the moment, there's no information on that, right? So if you look at the satellite right now, you have no idea if the satellite is beaming these beams at you or somewhere else. So we don't really know what is the power density other than these rough assumptions of, let's think that the thing is a sphere and radiates everywhere the same power, which is quite bad. So we also don't know the statistics of that, right? We have no idea how the statistics really look like. And we don't really know if there are some parameters that we can use for dependency. So we tried to produce a model for that. And the model, this graph is not really good, so let's go to that one. So for this model, what we said is, all right, we can know where the position of the satellites are, right? So we can simulate that in the sky. And we know what the arrangements of cells can look like, right? So if we do this, we just put cells on the ground, and we say the size of the cells are this and that, for example, 24 kilometers, I think, for Starlink. And then we can just place where the satellite is, and we can select different cells randomly. And if we have our point there in the middle, which is our radio telescope, one can start looking at the statistics of this and how you will start seeing satellites depending on where they're looking at. And because this is a statistical process, you do this many times, and then you get an idea of the power flux density and how that changes, right? Power flux density means the intensity of the emissions on the Earth, right? Forget about the receiver antenna for a moment. It's how intense this light is, for example, right? So if I'm here, sorry, if I'm outside of the light, I'm not receiving this intensity, right? This is the idea. How that changes, and you really don't know. So this is what this model is trying to look at. And if you see up there, that's the power flux density that is nominal for Starlink, right? So they say minus 180 something, doesn't matter. And we were using that value at the moment. But if you start seeing the spreading of all these points are each one of these simulations and looking at the satellite depending on the arrangement of these beams in only one channel. Right, so if you see all of this, the spread is really big. Right? It's really big because of that. Right? If all the beams are looking away from you, you're going to see very little power. Right, so we did this as a model. This is all a computation. And we produced this mean value. Let me check where am I? All right. Really late, but OK, so and we produced this mean value depending on the elevation of the satellite. And there are some interesting things already here that you can see that in lower elevations of satellites, this means satellites that are lower, close to the horizon, right? So you start here in less than 20 degrees there. And what this thing is basically telling you that satellites that are low in the horizon, they cannot point at you. And if you have read or seen a little bit on the filings of Starlink on how they work, it's because the beams cannot steer away so much, right? So if the satellite is lower in the horizon, and I'm looking at it like that, it cannot steer the beam so much to get it into my position. So that's what this curve is telling us, right? So when you get there, this elevation, 34 degrees, something like that, that's when the satellite can produce emissions in my way, right? So I'm starting to see more power. And then this thing is also more explained for when the satellite is going up, there's a much more spread. So the beams are also always looking or beaming somewhere else. So this is the model, all right? And we did the model, and then we said, all right, how we can try to prove this. And to prove this, of course, we need radio telescopes. And radio telescopes are not intended to do these things, right? We want to observe celestial sources. We want to do BLBI. We want to do BIGOS, as Vincenza was saying before. But we got lucky, and the Onsala Space Observatory was kind enough to collaborate with us, and they made available the Onsala twin telescopes for some time when, between scheduling of the observations of the telescopes, they said, all right, you can use your telescopes for a moment of time to do these observations because the telescopes can work at these frequencies. An interesting thing is that if you see there, SpaceX is not providing service in the Onsala Space Observatory. So that's something we took into consideration in the model. And if you remember that blue arrangement of cells, we can do this model just by taking cells from the middle. 5 minutes. Yeah, I think I'll make it. 3? Oh, no, come on, give me 5. All right. So, okay, so then we have the telescope now, and we need to figure out where the satellites are. And that, I said, we can do it. Yeah, we kind of can. So what we did is we thought of a technique. First, we said, well, how we leave the telescope there and see what happens. And we didn't see much. So we said, well, no, we need to think in some other way. So we said, how about we put the telescope where the satellite is coming, and we wait. And that kind of worked. So those horizontal lines are the position of the telescope, and the blue lines that kind of softly move are the position of the satellites. So we did that, and you see we got a lot of hits, of course, because, yeah, we did the math right, and the telescope points very well. So we got a lot of hits, and we were able to measure all these channels from Starlink emissions, right? Because they are providing their service, they are using their frequencies, so this is not talking about RFI or anything, it's trying to model the emissions, all right? So there you see 5 channels from Starlink from 11.5 gigahertz to 12.7, something like that. All right, so we did a lot of observations, not as many as we would like to, but telescope time is, of course, limited. And we, of course, calibrated the thing. I'm not going to go too much into that. But you see, that's the result we have. And yeah, I would like to compare, of course, that to the simulation and see if that makes sense or not. And we could see quite a good agreement on the simulation. Of course, fitting the parameters of the simulation, right? We had to change some things, and we said, all right, how about we change the number of beams we are calculating, and so on. And we could fit the simulation to the observations quite well here in low elevations, because we saw a lot of satellites here, right? Seeing satellites at higher elevations is much complicated because there are less of them, right? So that wasn't so easy. And that is why we think we have this dip in there, because we have much less observations. But we think that our model works quite well. So future applications, and I'll finish in a moment. All right, so the idea of this is to really be able to do realistic worst-case scenarios, right? If we need to understand how much power our antennas will receive when a satellite actually goes to the beam, you need to have a good model of the satellite, right? Then if there are very few satellites, for example, or you're looking at an area in the sky where you don't have so many satellites, great, you won't see any, and that's fine. But you need to have a way to say, all right, if there is a satellite and it goes through my beam, what is the statistics of the amount of power I will receive? So how much time, or what percentage of time will my receiver just saturate because the emission is too high, or will it produce intermodulation and stuff? So that's one of the things we can do. Of course, include this in radioastronomy studies. Probably use it in EPFD calculations. We are under discussion on that. It's not clear if we can use it or not, but that's going into the ITU, a little bit more technical. If anyone is interested, we can still discuss that. And just to finish, we are hiring in the team. So we are looking for a radio spectrum scientist. And I encourage, sorry, if anyone is looking for a change of job, something like that, you're all encouraged to apply. You can see the QR code there. Of course, the slides are available, and you can find them in the program. So thank you very much. Any questions this time?
Thank you very much, Federico. We have time for one question while Daniel comes up here. One question in the audience. If you wouldn't mind stating who you are when you pose the question, please.
Okay, very nice presentation with the measurements. I mean, this is very important. And I'm trying to plan something similar with ALMA. So this is definitely something we have to do. But just one question about the service, which is not offered, right? You have this map, and we look at the same map, and it is not offered in ALMA as well. So in the whole park, astronomical park, it is not in the map, so the service is not offered. We brought an antenna there, and there is the service. So do you know this, if in that place?
No.
Okay,
you
didn't try.
We did a completely uncoordinated measurement.
Okay.
So there was the possibility to try to talk to SpaceX and say, all right, what can you do? Can you move the beams and so on? We said, let's try to do this, like looking at the satellites and see what they're doing. There is the possibility that someone near the ONSA Space Observatory actually has Starlink and they are using it, and we really don't have a way to prove it, because it's quite complicated to do this kind of observations and understand the statistics and really where the beams were pointing at, because you have no idea, right? You make an observation of a satellite, and the beams can be here, there, and then you do another one, and they can be somewhere else. So yeah, that's a good point. What we are working right now is talking to SpaceX and also talking to Kraft and the European people. We are planning some observations coordinated, and that's the idea. So we might bring an actual terminal and know that some satellite is providing service, or know exactly which one is providing service, and also investigate some of the things also Chris was talking about, like the telescope is pointing there, give service with the satellite over there, and what's the power we receive, right? So that's interesting things to understand. Thank you.
Thank you. Let's thank Federico again.